Welcome to the last class of the fall semester for ITP485. I'm going to talk about instance rendering and compute shaders today. Now, the structure of this last class is that it builds directly into the final for this semester. For this semester, the final will have two parts. There'll be a written exam similar to what you've done before, and there will also be a program that you'll have to write very similar in structure to how the labs work. The content for that programming assignment will be based on today's lecture. So, right into part one, instanced rendering. Okay, well, here's a tree, right? Okay, what have I got here? There's a mesh. It's a regular geometry made of vertices, just like everything we've drawn so far. But one tree isn't enough. Is it ever? We're going to want a lot of trees. How many trees? Like a lot of trees. This scene here is made of duplicates of the same tree. This is only one mesh. That whole scene is just a bunch of copies of the same mesh. They've just been placed in different locations and rotated to different angles so they don't look identical. But they are. That's a pretty typical approach in a video game, is to reproduce the same graphic several times to make it look more than it really is. So, as we talk about how to draw that forest that I just had, let's imagine how it would happen. How would this go down in our rendering engine the way it stands right now? How do we render an individual object? We have something called a render obj, and there's a draw function on it. If you dig into what the code for that does, a render obj has a mesh has a vertex buffer, right? And so it goes through a chain of various things that each part sets up. But if you break it all down, and you write it down, we have a few things. Here we have a shader and a material. In our case, it's just textures, right? Well, really, the material is the combination of the shader and the textures. And then we have geometry. We're using indexed rendering, so we have a vertex buffer and an index buffer. And then we have some constants in the form of our object to world matrix. And then there's a draw command. It's a draw instanced command, and we pass in the number of vertices in our mesh. That's how we render. So first the mesh decides which shader it uses. So we set that shader to be active. We send that shader to the GPU. There are one or more textures that have to be set for that. Either maybe actually 0 or more. Some things could be untextured. But our objects tend to be textured. Most of them have one, but the normal maps have 2 textures on them. And then comes the vertex buffer. This is the stuff that's in the vertex buffer. The vertex buffer has an array of vertices and an array of indices. We need to send those to the GPU. And the render object has the object to world matrix for that object. And then we say draw. Now, if we wanted to make a forest, how would we do it? Well, we would say a bunch of render objects. In order to have this forest, they can share the same mesh. They share the same texture. We have that set up with the asset manager. But they each need their own object to world matrix, and that means each one's going to get its own draw call. Now, if we were really clever, we could realize that all the trees are using the same shader, they're all using the same texture, they're even all using that same vertex buffer and that same index buffer. We don't need to set those over and over. So if we thought about it, we could sort all of our objects by mesh and say, let's render objects that use the same mesh first, and then that would allow us to skip some of the redundant parts. We'll set the shader, we'll set the texture, we'll set the vertex buffer and the index buffer, but then those are not going to change for all the rest of the trees. We set it for the first tree, And then let's leave those be while we do tree after tree after tree after tree. The only thing that changes from object to object is the matrix. So here's what we'll do. We'll set up our geometry, set up our textures, and then we'll do set our constant matrix, do a draw. Set the new constant matrix, do another draw, set the new constant matrix, do another draw, etc., etc. We can go through our whole forest this way. And here, you'll notice we only sent the vertex buffer once, and we only sent the texture once. Hopefully, that'll save us some time, make the thing go a little bit faster. Unfortunately, we still have one draw per object, and the number of draw calls can actually be a bottleneck, particularly as the CPU tries to communicate all of this to the GPU. If we can crunch that down a little bit more, we can sometimes get a speed up. Now, those of you who've done real games before, maybe you're like in an AGP or an intermediate project, some of you may have explored this idea of mesh combine. That's when we take static objects in the scene, objects that aren't going to move, and we run a pre-process on them. And we say, hey, take these objects that are a bunch of separate objects that are all placed, they have different meshes maybe, they have different geometries on them, maybe they definitely have different matrices on them. Combine that all to one object. Take all the vertices out of them, transform them, and bake them all together into one big object. So now, when we draw this big old object, we set the shader, we set the textures, we set up the geometry, we set up the object to world matrix, and we draw. And then that's the whole thing. We make the whole forest one ginormous object. Okay, downsides. Your geometry buffers are really big. That's this stuff. That's the number of vertices. You got a lot of vertices in that one object. And also, this only works for objects that aren't going to move because, you know, we said we pre-processed this. So those trees aren't moving around. And, okay, they're trees, so they're not moving around. This is a reasonable approach. But those geometry buffers are really big, much bigger than they would have been in the other version. So that means we've traded, on the upside, it's only one draw call. On the downside, it's a big draw call. Also, we can't do frustum culling individually on the individual trees. You can only frustum cull now the whole thing. So there could be wins by doing this. A lot of times we get wins from this, especially with lots of little things. Let me do tangent. Woo! Flying off on tangent here. Tangent mode. If you have a tree that's made as, like, the trunk is an object, and maybe the leaves are individual objects, and maybe there's like flowers that somebody has stuck onto the tree in different places, you want to mesh combine that. You want to combine that into one thing instead of a bunch of little things. And that's because locally they are all one object. It's all compacted into the same place already. You'd want to mesh combine that because the frustum cull is going to, you know, I'm assuming we've got a forest of these trees. So when I'm looking at one tree, then there's another tree next to it, right? And so maybe the two trees shouldn't be combined as one tree, but this whole tree with all the parts stuck to it, all the leaves and twigs and flowers, anything that's not moving can be baked onto that one object. Okay, that'll be a win. Okay, what else can we do? Introducing a new concept called instanced rendering. What is that? Here's how we do instance rendering. We set the shader, set the textures, we set the geometry of a single mesh, now the original tree mesh. We set those geometries. And then we set up a new kind of data called instance data. The instance data is an array of all the object to world matrices. We take the object to world matrix of each tree and we stack that into an array of data, shove that at the GPU and say, hey, GPU, I want you to render this geometry for every one of these matrices in the array with a single draw command. We're going to say, hey, and draw it, and then you'll say, how many of those did you just give? Like how many matrices you gave. Okay, so on the GPU, it still has to run the vertex shader for all those vertices. It still has to transform all those objects and draw and rasterize. It has to run all the same number of pixels, same number of vertices, no matter how you slice it. The GPU has to process all that. But what did we save? We saved a lot of data pushed from the CPU to the GPU, and we saved a number of draw commands that were sent from the CPU to the GPU. Okay, so that's a useful thing where we can, with a single draw command, take one geometry buffer and a whole array of matrices and render that same geometry a whole bunch of times. For example, and we're going to see this is going to be the basis of the final project. For example, we could instance a bunch of particles. I've added a particle system to our engine, and each of these little, you can see the little individual smoke puffs are little individual rectangles. And so a rectangle, you know the rectangle, it's a very small little vertex buffer, a small little index buffer. That's what we're going to draw, but we're going to draw a lot of them. So we're going to instance our little rectangle all over the place. Okay, let's take a look at how that could work. I've got myself my little quad. It's two triangles, so I drew that like this. And in the center of the quad, I've marked that. And here's the texture. This is what I want. I want to take this little cloud puff thing, and I want to draw that onto my rectangle right there. So what are the vertices? The vertices are the four corners of the quad. That's simple enough. But each instance needs to be in a different location. So that's the instance data. The instance data is going to be where is the center of the quad. So I'm just going to give a single location in world space of where I want a quad to be. And I've added a little bit more information here. I've also added a size and an alpha so that I can make them different sizes and I can make them fade in and out. There's a couple of features that a couple of the many features that you expect in a real particle system. This is a stripped down, fit on one slide kind of a particle system. So that's all I've got in here. Okay. Now, let's take a look at this. I've circled here for us these two member variables in our input vertex structure. Look pretty familiar. We got the position in object space, right? Position in object space of the vertex and the UV coordinate for that vertex, right? These are per vertex data. And I've written here what I've got for the XY, the position coordinates. It's actually, you can look in there, I think it's YZ, I don't know, it's not important. These are the coordinates of the four corners of our mesh. And each vertex now is going to have a different copy of that. So this vertex is going to be there. This vertex has a slightly different position, and of course they have different UVs also. Okay, so I'm going to get 4 vertices to render. In fact, since it's a triangle, two triangles, I'm going to get 6 vertices. Right? 6 vertices are going to go through the vertex shader using these 4 positions. So what is this stuff down here? This stuff is where new things are happening. I've labeled those with the names instance in the front. Doesn't mean anything special to HLSL. That's just for us. That's for you and me to understand that this is the instance data. The data I had up here was my regular vertex data. These look like part of the vertex data, but they're not. That's instance data sitting there. And we'll see how I pulled that off in a minute. What's going to happen is I'm going to get the world position. This is the world position of the center of my instance. I will also get the size. This is how big it is. And also I've got an alpha thrown on there. Alpha is how fadey outy the thing is, how opaque I want this thing to be. So when I render a particular instance, one quad, I'm going to get two triangles, triangle, triangle, just like I always have. That's these two pieces of data, just like I always have. But all 6 vertices that go through the pipeline for those two triangles will have the exact same instance position, instance size, and instance alpha. That I'll get a vertex right here, get a vertex with a position, and then this centered instance pos, the size of it, and the alpha of it. Then I'll do the next position. The position will change, but the instance data will not change. Okay? Even though my structure, my input structure looks like a structure, I'm going to use my input layout with these semantics to say these 2 come from vertex data, these 3 come from instance data. So when I get another instance is going to come through the pipe, and once again it's going to have those exact same 4 vertices are going to come through exactly the same. And then, but the instance data now is going to be different for this new instance. I'm going to get a different position, maybe a different size for this new particle. And so that's what I'm going to do. And if we look down here at the shader itself, this is where the action is happening right there. What am I doing with that? All I'm doing is taking the size you asked for and multiplying it by the position. That's a little weird. What? Wait, what? Remember, the input position, that's this. This is that. The input position is in object space. So to scale it up or scale it down, I can just multiply it by a scale. Simple as that. So that's what that is. And then to put it into world space, I would normally multiply times a matrix, but I don't want to do a whole matrix. I just want to keep it like that and put it there. So I'm just adding the instance world space position. So that's coming from instance data, right there. Okay. Okay. So that's how that works. I should comment that this works because the camera in our game never rotates. So everything I've arranged my 4 vertices so that I've arranged the 4 vertices so that they are going to face the camera. And that's fine. A real particle system now would need another step of turning the particle to face the camera, and I'm just skipping it for simplicity. Like I said, I want this thing to fit on one slide, and there's really no need. That's not part of the final to talk about how to do that. I think we could work out the math of how to turn a particle to face. And yeah, maybe in a bit we'll talk about how we could use a geometry shader to pull this off. But for now, this will work. Okay, so let's take a look at how on the CPU side we send that data. So here's a little snip, and this will be in the starter code that I'm providing. If you look at how a particle emitter renders its particles, it does it like so. This part is just setting up the texture, and it looks exactly like we've done before. I've reused the diffuse slot. So if you've got a texture, set the texture active. Setting a blend state. I want it to fade in and out. We've talked about that during the Bloom lab, so that's the same thing. And then I upload my buffer. What is this? What buffer is this? This is my instance data right here. This is the instance data that contains not a full matrix in this case, but the position of each instance as an array. So I have an array of all my particles. The position of each particle is in the array. I'm throwing that to the GPU and calling that my instance data. Okay, I need to tell the GPU what the stride of my data is. And you'll remember this from before. We used this same command before. You may have to dig pretty deep or maybe just roll back through your code. Take a look at your code. How did we draw a vertex buffer? A regular vertex buffer. We only gave it one vertex buffer and we gave it an index buffer. So here's your index buffer again, just like we had before. But the vertex buffer now, instead of giving one buffer, I'm giving two. And if you look at your vertex buffer draw, you'll see this exact same line, and you'll see you've put your strides and you've put your offsets in. You'll see all that's there, only we gave it only one buffer. That was the vertex buffer. So I'm giving that. I'm giving the vertex buffer. Here we go. Here's my vertex buffer. And then I'm also giving it a second buffer. The second buffer is my instance data buffer. So I give it my vertex data size and this is my instance data size right there. So that's what I do. I just say, hey, I'm giving you two buffers. I'm giving you the first one and the second one, blang, zoom, and we're good to go. You might notice I got an S underscore on the front of my vertex buffer. That means it's a static. And why is that? It's because every particle in the whole engine all uses the same quad. It's just a quad, right? It's just that quad I gave, minus 0.5 to 0.5 size. That's it. And so I only need one vertex buffer for all of my particles. Okay. So then last here, if you are looking at your vertex buffer draw function, you'll see that there's a draw indexed to kick it off. And so you won't be too surprised. We have draw indexed instanced, where this is the number of indices. It's a quad, so it's two triangles, 6 indices. The next argument is the number of instances we want. So there you go. All right, we'll come back. I'm going to stop the video here. I'm going to cut it off. There'll be a second video where we talk about compute shaders and then discuss how we're going to launch into the final project.